So I've done up some stuff with these TP-Link Kasa smart plugs, and I'll have links to the code below. So far, I've done a few individual programs that do stuff like, turn the plug off and on. I did one that specifically clears the location data stored in the plug. And I've done a first draft on a file system to control them. But in the meantime, I got one of these. This is a Kasa power strip. And digging into this is making me rethink how I want the file system to be laid out. I also found some example code that allowed for doing broadcast packets to do discovery. So my previous Wiz light bulb system required adding the light bulbs to NDB local, but a automatic discovery system would be nicer. However, I ran into a snag with that. So first off, I'll go over the individual programs to give some basics on what it takes to talk to these devices. So at the top here, I have like sort of a raw JSON string set up as a macro. This is what the plug expects when the command to turn it on is sent. So this allows electricity to flow through the plug, powering whatever is plugged into it. These programs are really rudimentary. I don't have a lot of error checking going on right now. So if I go down to main here, all right, so I'm going to be taking the first argument, and that's going to be the name of a plug according to the the network database. So this is assuming that I'm using the NDB local to store the names of the devices. I set up a dial to start the network connection, and then I put the on string into a buffer here, and sent it off to go do the encryption. So the encryption is fairly simple. Details on it can be found in a paper I linked in my previous videos, so I'll put another link below and this one to it. So I do an XOR with this key here on the first character that comes in. That character then becomes the next key. Then I enter that character into this little buffer here I have to hold it. And it just loops through for however many characters are sent over. So I do have a thing where I pass an argument on how many characters the line is, and it'll go through all of them. So when that is done, the Kasa device usually expects the commands, especially when sent over TCP, to be prefixed to the length of the string. Like I said usually because there is an exception I'll get to later. This integer is expected to be what's called network order, which is big Endian. I'm doing most of my testing on little Endian Intel and ARM systems, so I flip it around. Again, another place I should do some error checking here in the off chance that this is being run on a big Endian system, but currently I'm one of the few people who actually boots 9front on big Endian systems. So I'm just going to do a raw flip on the byte order there. So get back down to main. So I do the encoding. I then write it off to the file descriptor provided by dial. So I have to add 4 to it because it's now 4 bytes longer because of that size prefix. Make sure that I clear out the buffers for the response. I wait a little bit for the response to come back, and then read in the response, and then I gotta go ahead to the decryption. So the decryption works like encryption but backwards. We're using the same key here. Since this comes with a size prefix, I just go in 4 bytes. Again, another point where I could do some extra error checking to make sure that that value does correspond to the actual length of the string. But anyway, for now, I'm just skipping that. So move again, subtract the 4 bytes from the size, and then just loop through. And the same thing, we're taking the key, doing an XOR to get the value back out, and eventually put it into my outbound buffer here. So back down to main again. So once I decrypt it, I get back a JSON string. I run that through some code using 9front's JSON library to make a more readable output for it. And then just, provided it actually worked, I'll print that to screen, and then exit out. And now I'll go ahead and run some of these so you can see what they look like. So I got my bulb here. It's currently, the power is on the switch here, but I have the power turned off at the plug, so I can do Kasa on plug 2. And that turned it on. It'll read back, the code I have will read back, the response. In this case, anything that works just comes back with a response saying error code 0, so it reads that back. I can turn it back off if I want. It'd be Kasa off on plug 2. Same sort of thing. I can do, let's see, it's the Kasa info. Or actually, I'll turn it back on, so Kasa on plug 2. Kasa info on plug 2. So we can see here, I ended up zeroing out the location data that was stored in there. So I could quickly go over that code too. So that would be in the Kasa no look. So here we can see that would be the string descend, where basically it does this set dev location, and then you could just put them as 0. For some reason, it takes 2 different ones, and if I remember right, the location I has to be like a multiplied by 10,000 based on whatever's put in the other ones. So I'm not really sure on the reason for that, but it does have it. And so all it does is take that, put it in, and again, like the others, you can put in the name of the bulb for your first argument. It sets it up and just basically runs through the same sort of thing as all the others. So most of these are copy and pasted. If I was going to do it again, I'd probably actually set up a separate file that holds all the encryption stuff and pull that in through with a header file and link them together. All right, so now I'll go over what I have so far for the file system. Here's the code for that. And I copied a lot of this just basically from the WizBulb file system I did before. Being that, like the WizBulbs, I'm communicating with something over the network. They speak with JSON strings, so just basically copy-pasted a lot of that and modified it to my needs. However, after playing with these plugs for a bit, I'm going to have to do some more work on making it work nicer. Much of what the individual programs does is going to be called in this, here it is, call Kasa. So this is basically handling what was main in a lot of those other programs, where it handles the dial, it does the encryptions. Yeah, there's the encryption. Here's the dial. It writes it out, waits a bit, reads it back, calls the decryption, and sends everything on its way. So by the time this is run, you send in a JSON string, it handles everything else, it spits back out a JSON string that could be handled later. On the actual file system end, let's see, I start with fs start. And here, again, I'm using NDB local entries with an added Kasa key to parse out the system names for use as file names in this file system. I allocate a file tree, be here, and add a directory named Kasa. And then I open up NDB, and I loop through everything that has Kasa equals plug as the values, pull out the sysname for it, and use that to create a file name, and loop through until I'm done finding, until there's no more bulbs get returned with Kasa equals plug in it. And then I close up the NDB file. And with that, I'll have a directory called Kasa. In there should be files named after all the plugs listed in my NDB. And on the read end here, read request comes in. This is all speaking 9p again. I basically just run that call Kasa with the name of the file. That's pulled in here. And I just send it that get sysinfo string I already have a macro for. So that sends that back. I parse back whatever reply comes back, because now it's just a plain JSON string. Again, need to do some better error checking here. And it will just print that value to screen. So I go up here. What I'm using for the info, I found out I can layer in several things. So it's going to do the basic get sysinfo, which will return the name of the device, its MAC address, all that other stuff, and also run the e-meter stuff. Just get real time, and that'll come back with the also append onto it the energy usage. Let's head back down to read here. Yeah, that's basically it though. So it's gonna call the bulb with that, parse back the JSON, and read it back out to the screen as a read operation. On the right end, we're going to be pulling in the data coming in on the 9p request. So you're obviously going to write some text into this. It's going to fetch that. And we run this make bulb command. This doesn't do a whole lot right now. I'm just basically looking for on and off, and I'll just send a prepackaged macro I have for sending the on and off command. But later I could add on some other things to, say, turn the little LED off and on, or other options. But haven't quite figured that out yet, what exactly I'm going to put into there. But anyway, I turn this into a command, or figure out what the command's going to be. I'm going to call the bulb with the command that got made, wait back for a reply. If I get a reply, I'm going to parse it. If I get an error on this, it'll put the no bulb into the error, and then jump down here and respond with the error message. So if that doesn't get set, error is nil, and that means the 9p system will know that there was just no error, and it will instead print back. Actually, this won't print back anything. So there's no actual response to a write unless there's an error. So I'll go ahead and run what I got so far here. So it's called testfs. This will automatically put it in /n. So I'll go to n Kasa. And I have my two plugs here. This one here is plug number 2. So I can go ahead and read it. That's cat plug 2. And we come back with a whole bunch of data. And this sort of gets me to my first issue I'm kind of having, is that these things are really chatty. Like, you get back like a device ID, an OEM ID, a hardware ID, a model name. That's kind of useful to keep. Now that I've blanked out the latitude and longitude, I don't really need those. Right here's the signal strength. That's still useful. Alias is a name that can be set from the app that comes with it, and that stays with the thing, so that can be kind of useful. Get to that later on. But yeah, there's just a bunch of stuff that just sort of clutters up the screen I don't really need. As you can see down here, I have the the current power usage on it. So if I echo off into plug 2, you can see that turned off the bulb. And now when I read it, this one here said it was pulling like 33 milliamps at about almost 4 watts here, and now it's not pulling any power at all. So the e-meter does work. The last time I did my previous video, I was using a bulb that used even less power. It seemed to not pull it in at all, so I found an actual old incandescent bulb to test this on. So yep, there it is. We can actually read from the bulb. We can turn it off and on, and that's basically where I'm at with that right now. So definitely something I want to do for my first thing is to rework the JSON parser I have to pick out more individual stuff, I'll probably need to do set up some sort of struct with the data I actually need, run the parser, put pointers, fill in some pointers in that to just what I want, and then have the actual read function just go off of that instead of the raw JSON string, because it just contains too much just sort of garbage info. So going off the all that extra info that I'm gonna have to parse through, this is the thing that kind of changed my mind on how I want to do this when it came to that power strip. So I have a thing to read the power strip here, and it comes back with a whole lot of stuff. So the power strips work a little different than the plugs. So not only does it have a whole bunch of different data, but then to send a command to it, it has to be prefixed with, I think it was a child ID, and then the rest of the JSON string. So what I'm thinking of is I'll probably want to do the strip, because it's still considered an individual device. So if I do this through my NDB local, the strip is one device with one IP address. I'll probably have to put in another sort of key value pair in there, so that my file system knows, hey, this is a strip, and make the strip name a directory name instead of a file name like it does for the plugs, and then fill in that directory with file names for each individual plug on that strip. So that's what I'm leaning towards with that right now. Let's see here. And then the other thing was playing around with this, I found that, let's see if I can find it in here. Like here's one of them, alias strip 1, whereas all these other aliases are going to be named like plug 2, plug 3, and so on. That one I actually changed using the little phone app that you can get for these things. And so this made me think, hey, instead of using file names from the from NDB, I could actually use these as file names, which would be an extra level of, during the file system startup where I call all the devices, pull back this alias name, and use that to set the name also. And that also came to another issue where it's like, well, if I'm going to not use NDB, is there another way that I can call these devices? And there is. These things do have a way to do broadcasts. So this was set up a little different. I tried writing my own code for it. And I did it a variety of ways. One of the things I found out was you could send the command with no size prefix as a UDP packet. So all the stuff I'm doing right now is TCP. If you send a UDP packet, no size prefix with get sysinfo, all the bulbs on your local network or in range of the broadcast would respond back. I couldn't get it to work though, so I kept sending it, wouldn't get any response back. I did find a project someone did they wrote it in Python on Linux, so I downloaded that, fired it up, and it would work. So I could send out a broadcast and it would come back with all the information on the plugs and the strips. Fired up Wireshark to find out what exactly they're doing different from me, and it turned out they are using a don't fragment flag that's part of the IP standard, so it's in the IP frame. Went looking around, this seems to be fairly common with IoT devices. I guess the manufacturer of these these devices are so simple a lot of times, they don't want to deal with fragmented packets, and that's just a way to do that according to the IP standard. If any packet that has the don't fragment flag, if it comes to a place where it's going to get fragmented, it's just supposed to be dropped. So digging through 9front though, they don't seem to have an easy way to set this flag. Asking the developers, they're just sort of like, well, why would you want to? Because again, getting your packets fragmented going across the internet is very common. If you set this flag and you try to talk across the internet, there's a good chance your packet will just get dropped silently. And so no one's bothered to set this as an option. The other thing is since it's in the IP stack, if you turn this on, it would send all your packets as don't fragment. And that's not really what I want in this case. I want basically one individual UDP packet from a specific port to have this flag, and no others. So to get that set up, I'd actually really have to dig into the IDP and UDP stack for 9front and set up a system where I could say, have a specific UDP port, temporarily set this flag, let the IP stack know to put that flag because it's in the IP frame, not in the UDP. And then send off, my broadcast and have it function correctly. It's either that or I'd have to handcraft a packet and feed it directly into the IP stack, which is also not fun. So it's looking like setting up Discovery will be a project for another day. So in the meantime, I'll probably be, just sort of setting these as my own personalized key value pairs in NDB local. So anyway, I'll put up the code that I have finished already. I'll put it up on GitHub and have a link to that in the description, along with some of the previous work I did and the papers about the details on the security or lack thereof on these devices. And as usual, have fun.